Hello, team, and welcome to Science Side Up. This is not my normal intro. Why is this not my normal intro, you ask? Excellent question. It's because I have found, I think, the dumbest thing I've ever read, and it took me a long time to figure out how dumb it was because I didn't think it could be that dumb. And yet, here we are. And yes, I am currently wrapped in a blanket. I'm wrapped in a quilt my mom made me for Christmas for both warmth and comfort. It's really cool. It's she hand quilted into it math symbols, and there's a proof for Pythagorean's theorem quilted into this. If you're wondering if I came to my nerdiness honestly or not. Okay. Sorry, this is Journal Club, and now you're here and you have to suffer with me. Okay, this is what we've been doing in Journal Club, everyone. This is what we've been doing. We've been reading papers like you do in a journal club. And okay, this is the paper we've been reading. This heat problems associated with the Genesis flood model, introduction and thermal boundary conditions. So he's going through why the thermal boundary condition for any heat removal thing has to have no more than the ocean warming no more than being warmer than 13 degrees Celsius. Blah, 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 blah. That's fine. So he's explaining one of the data sets he uses. And that's this principles of oxygen isotope paleothermometry. So this is, hey, oxygen 18 relative to oxygen 16 concentrations in marine stuff. So both in marine critters with that incorporate oxygen. So anything with calcium carbonate in it. And also ice cores are going to preserve these ratios of oxygen 18 to oxygen 16. And he goes through why you would have more oxygen 18 as a function of temperature for this, that, and the other. Okay, cool. And so as part of that, he's explaining this bit. The oxygen 18 value in seawater and hence in marine fossils becomes a proxy for total ice volume. High values of oxygen 18 in the oceans imply large ice volumes. And then this effect is first established by Shackleton. I told you guys Shackleton is a very famous in the geophysics world. He has a crater named after him on the moon's south pole. It's called Shackleton Crater. Yeah. And then he is one of the authors on this key paper in 1976, which is establishing Milankovitch cycles. Milankovitch cycles are an orbital dynamics thing. We know that over long periods of time, the eccentricity of Earth's orbit changes and the tilt of our axis. So that's actually the obliquity of our axis. So the Earth doesn't rotate right, Earth's axis of rotation is not perpendicular to our axis by which we rotate around the sun. It's off by 23.5 degrees. And that angle changes with time, and it has a periodicity of 70,000 years ish. And the eccentricity has a periodicity of 100,000 years. And then there's this, the other one is axial tilt, which is a wobble. And it, that one has a periodicity of, so basically our axis of rotation precesses around over a 40,000 period of time. And that's going to have differences in how the northern and the southern hemispheres climate there'll be differences between those. But we're going to talk about axial tilt, not axial tilt. My gosh, we're going to talk about obliquity. Because, so I was reading this, and then this author in this heat problem paper, talks about hey, I'm not going to get into the details here, but there's this other series of papers that talks from creationism land that explains all the problems with this big Milankovitch cycle thing. And I want you guys to just read the title of this paper. Revisiting an iconic argument for Milankovitch climate forcing. Should this very famous 1976 Shackleton paper, Pacemaker of the Ice Ages paper, be retracted? And I cannot, with the hubris of that title, right? That is the hubris of that title. One, if a paper does good science and presents a theory that is later proven to be like not true by future work, you still don't retract the paper. The only reason you would retract a paper is if like you did a bad job, right? If your methodology was bad or your reasoning was bad, right? You can have good methodology and good conclusions that's then like overturned by better data later, right? And that hasn't happened, by the way. Every time we look into Milankovitch cycles, right, we're reconvinced that they exist. And sorry, if people don't know, Milankovitch cycles are attributed to periodic ice ages in Earth's past, right? So Earth, turns out, has an ice age about every 70-ish thousand years, right? We have periodic ice ages in our history that's related to these orbital cycles. This is one of the most well-known and frankly easiest to model and predict climate forcings that exists, right? And weather is my thing. That's what my PhD is in. Have I been editing my dissertation all day? And that's also why I'm a little manic right now? Yes. But here we go. We're not to the dumb yet. So I was reading this paper and I thought, I was like looking through it and I was wondering, should we read this in like journal club? And I got to the dumb. And again, it took me a while to figure out how dumb it was. Because it is this man who, and by the way, notice that this is papers part 1 in a 3-part series, tries to take down like well-established known science, right? This would be hard to disprove because there is so much good evidence that supports it. And he's just like, here's a 3-page paper of why they should retract this, right? And team, when I tell you that this man who wrote this paper, what's his name? Jake Herbert, the hubris of Herbert. That's what this should be titled. Jake Herbert doesn't understand how seasons work. Let me be very clear. Let me say that again. In reading this paper, in reading his work, trying to overturn like fundamental science, it is revealed to me after much wailing and gnashing of teeth that our author, Jakey Poo, doesn't understand why the winter is cold and the summer is hot. He doesn't know. Guys, he thinks that, okay, I'm going to show you. I'm going to prove it to you because you don't believe me, do you? You're like, everybody knows how seasons works. We learned that in like 1st grade. I'm pretty sure Miss Frizzle taught that to me. You're not wrong. You're not wrong. I'm sorry. I got heated there for a moment. Let me do here, there. That's better. My face isn't buried in a corner, though maybe it should be. Okay. So here we go. He's like summarizing the paper, and using some like, funny, he's like, sorry, the hubris, like the writing in this paper is just dripping with Jakey Poo's hubris. Okay. Like this, despite the fact that the Milankovitch hypothesis had been rejected by previous generations of scientists. And then he cites one paper that's published in 1982. I haven't even checked this paper, but the original paper is published in 1976, right? And you know what's a very healthy, normal thing to do in the scientific field? Offer critique right? That's not like it's been rejected by previous generations of science, right? That is the scientific process in action, right? It's like, should we accept this? And turns out it is now widely accepted as a result of the pacemaker paper, right? That's what he's referring to, this pacemaker of the ice ages, right? Um, um, okay, the papers, and like, it's not, the pacemaker paper like proposes this idea, and then the community rigorously checks their work, and we're like, oh yeah, you guys are right, that's real cool. That's it, like, the end, you know what I mean? And like, some people are like, but maybe not right. And right, like, again, that is the normal scientific process. But again, listen to some of this guy's like language. The paper's authors performed power spectrum analysis on data having presumed climate significance. Presumed climate significance of a temperature analog? Yeah, honey boo child, temperature is a climate variable. That's not something we presume, right? That's like, explain to me how you would not presume that temperature is a climate variable, and that now if you want to be like planktonic foraminiferal oxygen isotope ratios, if you want to argue that like oxygen 18 ratios in marine like critters isn't a temperature analog, like, again, my guy, there's a lot of work that says that's true, right? There's a lot of work that says that's true. And so you would need to demonstrate that all of that work is wrong. You can't just say the paper's authors presumed these were climatically important variables, right? Like, that's, oh my gosh. They didn't presume it, my guy. They like based their work on the work of other scientists, right? We're building on top of each other. Like sediment that you might find at the bottom of the ocean, of ocean critters that die and leave a record over time of oxygen 18 to 16 ratios. Building on top of each other. Okay. I'm wrapping myself in my quilt. This is partially because it is kind of chilly here, and my very sweet boy Chester, who is the Velcro dog, and I am his human. He is sleeping on his blanket, and I turned the space heater onto him so he could be warm and cozy. And he's very happy right now. Okay. Okay. So, by the way, this is the data that they had, which I think is really cool, but we can talk about that. This is the temperature data, or sorry, this is the oxygen 18 data. Okay, so the Milankovitch orbital cycles, the Milankovitch or astronomical hypothesis, it's just called the Milankovitch cycles, my guy, like, please use the right terminology, posits that subtle changes in seasonal and latitudinal distribution of sunlight have paced the Pleistocene ice ages, and by extension, according to current uniformitarianism thinking noted earlier, have also paced the deposition of the sedimentary record even hundreds of millions of years prior. The amount of summer sunlight at 65 degrees north, generally considered to be the driver for these climate variations, although others have argued that sunlight variations at other latitudes and seasons are actually responsible. Okay, these changes in solar insolation, in turn, thought to be caused by changes in the Earth's orbital and rotational motions occurring slowly over many tens of thousands of years. He dropped a little hint of the dumb. Did you guys find it yet? Okay. Sorry. Okay. So this is explaining the change in obliquity. We go from 22.1 degrees to 24.5 and back again over 41,000 years. I thought that was the 70. Anyway, I'm probably getting the period. I think I said 70,000 years earlier. I might have gotten the periodicity wrong. Maybe he has the periodicity wrong. It doesn't matter at this point. Okay. So this change in the shape of the Earth's orbit is characterized by cycles with periods about 405 and 100,000 years. Actually, Milankovitch insulation theories predict that the 100,000 year cycle should actually be proposed of 2 cycles. Yeah, so like this is the eccentricity brought in. Sorry, my phone is making an alarming sound. Ah, okay. Sorry, it's an amber alert for the area. Yeah. Okay, cool. That's startling. If anybody knows, I'm trying to figure out how to make all my kitchen appliances make less noise. Anyway, okay, so blah, 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 blah. So this is just talking about, like, there's changes in eccentricity that affect it, and, like, we know the Milankovitch cycles, there's 3 of them, and I think that's what he's summarizing right there. Okay. Since okay, I think this is where it was. Hence, according to the Milankovitch hypothesis, one might expect Earth's climate to be cyclic, alternating between ice ages and warmer interglacial periods. Since Pacemaker purported to show evidence for the last of these 3 cycles, it is viewed as having confirmed the Milankovitch hypothesis. Okay. Okay. Here we go. Examination of figures 5 and 6 in Pacemaker show that the spectral peaks corresponding to the periods of 100,000 years are generally much more prominent than the peaks corresponding to the 41 and 23,000 years year cycles. Yet according to solar insolation calculations, so solar insolation, that is like how much energy from the sun makes it to planet Earth and can be absorbed by planet Earth. Or a planet, right? Or a celestial body. It's not, that term is not unique to Earth. Variations in the distribution of sunlight due to the eccentricity are extremely small. Hence, of all the astronomical cycles, the eccentricity cycle should have the weakest effect on the climate. Okay. So, that's not the dumb part that I was trying to get to. I feel like that was actually earlier and I skipped over it in confusion and rage. The 100,000 year thing, that is, if our eccentricity increases, our average distance from the sun increases. And so therefore we get less incoming solar radiation. And that's really it. And that's it. Sorry, it's not more complicated than that. But I wanted to talk about what he really doesn't understand is the obliquity. That's where I found the dumbest dumb. Okay, hold on. Where was it? Because I got so mad I rage quit reading it. Okay. Okay. Where is it? Because I read it here. Was it in his summary? Introduction. Okay. Okay. Just goes through all the background. No. This is it. Oh my gosh. Okay, this is it. Sorry, this is the line. This is the line. This is the line. The most obvious problem with the Milankovitch hypothesis is that it is not clear how ice ages can plausibly be called by very small decreases in high latitude solar insolation. Okay. Okay. Team, let me show you. He'll show you what he means by that. Okay, because we're just going to show a calculation for solar insolation. Oh my God. Okay, so what that means, that sentence, what that means is that he thinks that the difference in like ice age versus not ice age is the increased distance, or the decreased distance to the sun because of the tilt. So when right now we're tilted like this, if we tilt less, the closer to upright we are, the more likely an ice age is. Why is that, you ask? Excellent question. Excellent question. Oh my goodness. Okay, so why is that? Let me just explain. Okay. So, the tilt of our axis determines a couple things. It determines where the sun is directly overhead, right? Changes over the course of a year. So on the equinoxes, the sun, right, like at like the noon position of the sun, where the sun is directly overhead at 12 noon, that is at the equator, right? On the equinoxes, that is directly at the equator. On the at the northern hemisphere summer, right? So my northern hemisphere summer equinox, the sun is directly overhead at the Tropic of Cancer is the northern hemisphere. Yeah, which is at that like 23.5 degrees latitude. Oh my gosh, that's exactly the degrees of our tilt. It's like those things are related. And at the winter solstice, northern hemisphere winter solstice, the sun is directly overhead at noon at the -23. That'd be the Tropic of Capricorn, unless I got those backwards because I'm doing this off the top of my head in a ragey rant. Okay, so that angle, right, determines this sort of how far north that directly overhead is. What else does that angle determine, right? That angle also determines how far south the like midnight sun is gonna go, right? So if we were tilted less, right? If our angle was closer to straight up and down, then like the minimum latitude that's going to experience like 24-hour night or the midnight sun, right? That changes, right? The closer to upright we are, the shallower that angle, the further south that latitude, right? Okay, so maybe that's making sense now. So this is fundamentally like, is winter cold because we're this much further away from the sun, or is winter cold because the sun's not up as long and therefore that area is getting more oblique incoming solar radiation, right? Angle matters. Who would have thought? Angle matters and time matters, right? So the more oblique the angle, the less straight overhead the sun is, the less of that energy you get, the less of a fraction, and then the less amount of time the sun is up, the less energy you're absorbing, and so it's colder. And that's why winter happens, right? doesn't have to do with how close we are to the sun, right? So if we change our angle, right? And then, so like right now, at the winter solstice, Boston gets about 9 hours of sunlight. And on the summer solstice, it gets about 15 hours of sunlight. On the equinoxes, it should get 12. Okay. So if that angle was shallower, then Boston would receive, I don't know the exact number, but less hours of sunlight in the winter, right? It would be less than 9. It goes into 8, right? And so if you take 1 less hour of incoming solar radiation, and the incoming solar radiation that you're getting is at a sharper angle, and so you're getting less of the energy, right? Because of trigonometry, it's just trig. It's just trig and angles. It's not that hard, right? No, I shouldn't take that off. It's cold. I want my comfort blanket. Yeah, that's what causes it. Not a significant change in not what he said. What did he say? Hold on. We're going to look at that. I'm going to show you that solar insolation calculation. Let me do that. I know I'm all over the place. I'm sorry, team. I'm big mad. I'm big mad and I'm big sad. Because of the stupid. And the stupid and the hubris, right? These are things we don't like. We really don't like people who are confident in their ignorance, right? That's what's maddening. That is what is maddening, my friends. Okay. Stop sharing that screen. You can't see it because I hit it on StreamYard here, and I'm gonna present a new one. We're gonna. Oh my gosh. Okay. No time, Maddie. It's 8 p.m. Why are you yawning? My gosh. Okay. Here we go. Sharing not the infinite window, but we're gonna do a thing, and it is solar insolation. Solar insolation. The actual amount of solar radiation incident upon a unit horizontal surface over a specified time for a given locality. It depends on the solar zenith angle and also on the ratio of the actual distance to the mean distance of the Earth from the sun. So this zenith angle matters. And again, you know what else matters? Time. Okay, so, okay, so here's a nice little diagram, right? Again, is the distance from the sun at the equator versus the pole noticeable? No, that's negligible, right? But look at like the obliquity of that angle, right? It's not coming straight down. It's going across like this, right? And so like less of that total energy is deposited. So I would love to see their little calculations for the small change in solar insolation, like small changes where, and also again, multiply that, like how does the time change, right? Because there's other things that affect it. And solar insolation, like to, yeah, let's do formula. So that's not what I wanted to do. I'm so sorry. I wanted to do black body temperature. Peak black body temperature formula. Okay. Am I still sharing this? I think so. Again, I'm sorry for the rage. Okay. Oh my gosh. Am I crazy? Am I Googling the wrong thing? I don't want to find the peak wavelength. I want to know, not peak black body. Oh, it's the surface temperature of a black body. That's what I want. Yeah. Okay. Sorry. This, we're going to relate the energy, the energy per unit time. So that the power is of like a body, the energy emitted per unit time by a body is equal to this like the Boltzmann constant times temperature to the 4th, right? So this energy having a relationship to temperature to the fourth is also important here. Because if this is a true black body, then with like no atmosphere, then the incoming energy has to be the same as the outgoing energy. And the difference is like it's the energy, it's like per unit area as well. So you have to look at how much is absorbed and then how is it emitted. And then there's like the surface temperature. So that we can relate the incoming energy of the sun, or rather the incoming power, which again is proportionate to, is related to time. That's energy per time. And so if the sun's only up for 8 hours a day, right? That matters a lot when you're doing this calculation. And then that amount of energy is related to temperature to the fourth, right? Sorry, you can have a small change in temperature be related, I'm sorry, I was like ranting and then I lost my thought and I'm like, now I've confused big and small in my brain. So temperature is going to be proportionate, surface temperature is going to be proportionate to the fourth root of that energy. But anyway, so I was thinking of that upside down, but my argument about the time being thing is the same. So, okay, I think we're going to stop with that for a second and I'm going to collect myself. And again, okay. So let me show that. Let's pull up the paper again. This one. Yeah, this one. Okay. So it's not clear how ice ages can plausibly be caused by a small decrease in high latitude solar insolation. To me, that says, again, he thinks that like different temperature differences between seasons are related to physical distance from the sun, right? And is not taking into account, he may not be taking into account the angle, right? The zenith angle that you need in that insolation calculation. And it definitely doesn't seem like he's taking into account amount of time the sun is up, right? Because that matters. That matters a whole lot here. And so now, even as it is now in here on good old planet Earth, where we are in the year of our Lord 2024, there are still permanent ice sheets, right? So this problem actually, like, there's some climate feedback cycles. So there's these like positive feedback loops that are absolutely in play here because this is polar stuff. I guess I know a lot about polar stuff, you guys. Oh my gosh. Because that's like what my dissertation's in, is like Arctic weather. Okay, so here's what's happening. Here's another, then there's other compounding factors, and so let's get into that. So let's say we have a particularly cold year. Okay, let's just say it's gonna be a cold year. And so northern, and I'm just going to focus on the northern hemisphere. I'm sorry, southern hemisphere. I don't mean to forget about you guys, but I'm just more familiar with northern hemisphere. So in the winter, in the polar and far north regions, right? So like northern parts of Canada and Siberia, right? In those regions, it snows, right? And it rains, and then it's below freezing, and so stuff freezes, right? And right, there's things that we know that we have that are frozen year round. Glaciers, parts of our sea ice are still frozen year round. We have permafrost, right? We have land ice, or we have like ground that remains frozen year round. Okay. So bear with me. We have a particularly cold, wet winter. Okay. And so this year, this imaginary year we're talking about, we added ice. So at the, towards the end of the winter, we added ice to our glaciers. We added sea ice. By the way, that sea ice addition, that happens all the time. That happens every year. It has a cycle. So sea ice grows and then melts in the summer, right? So we've added ice. We've added to that permafrost, right? But there is more ice at the end of the winter than there was at the start of the winter. And let's say for some freaky reason, we have a kind of cold summer. And so we don't lose as much ice as we normally do. And so then the second winter we're going into, we have more ice at the start of it than we did at the start of the winter before, right? And now, okay, so what happens now? All right, so the more ice you have, the shinier the surface, which means the Earth's albedo is going to go up. Currently, at least in the polar regions, it's regional albedo. So globally, the Earth's albedo is about 0.3. 0.3 is how this albedo measures how shiny something is. A 1 would be perfectly shiny, and a 0 would be not shiny at all. So a 1 would be a perfect mirror. And so in a perfect mirror, all incoming light, EM radiation, reflects off the mirror and none of it is absorbed. If albedo is a 0, all incoming light, all incoming EM radiation is absorbed and none of it is reflected. So globally, Earth's albedo is about 0.3, which means 30% of the incoming light gets reflected back to space and not absorbed by the planet. But ice, the polar regions in the winter at least, has an albedo closer to 0.7. I feel a need to look that up. I think that's close to right. It's higher than the global average, and I'm pretty darn sure it's 0.7. But like, don't cite me as a source on that, you know? Okay. So this is called the ice albedo effect. I actually have a video on it if you want to look at that. So more ice means shinier, right? Shinier means more energy reflected back to space that doesn't get absorbed and doesn't add to the surface heating, okay? And so therefore, the shinier it is, the more ice, the colder it's going to be. And so then we're able to make even more ice, right? And then, oh my gosh, now this winter we have even more ice. And so going into the summer, even less incoming radiation, even more of that incoming sunlight gets reflected back to space, doesn't get absorbed, doesn't melt the ice. So it's a positive feedback loop, right? The more ice we have, the more ice we're going to make. And actually the opposite is also true. We see this feedback happening a lot right now. The less ice we have, the faster we lose it. Which is why like the Arctic is warming at twice the rate of the rest of the planet, primarily because of this ice albedo effect. Okay. So this is kind of how you can get, pun intended, I guess, a snowball effect going into an ice age. Of the more ice we make, the more ice we're going to have, and then the higher the Earth's albedo. And so again, just the colder it's going to continue to be, even affecting in the summers, right? Because that albedo, it's going to affect the Earth's like full annual albedo. There'll still be seasonal cycles, right? Summer is still going to be warmer than winter. Ice will still melt in certain regions, but that's all part of it. And yes, if you increase Earth's eccentricity and you increase our average distance from the sun over long periods of time, like tens of thousands of years, that's gonna be important. That's gonna have a noticeable effect. Same with that whole obliquity, right? And again, right, by saying wrong. Why did I click that button? That's not the button I want. I want this button. By saying that it is not clear how ice ages can be caused by very small decreases in high latitude solar insolation, then explain to me how seasons work. We have huge differences in average temperature between summer and winter, right, at those high latitudes. Now, yes, hey, guess what? If you're at the equator, your average temperature on December 21st versus your average temperature on like June 21st, rough dates for the solstices, it's going to be about the same. You get bigger temperature differences between the seasons the higher your latitude, right? So Boston in August is 80 degrees. Boston in February is cold, right? It's cold. And if we're going to have milder summers, right? Think about just a milder summer, how that would affect everything, because that means less melt, right? That means so many things. That's going to affect everything. And this is paper 1 of 3, and he doesn't appear to know how seasons work. And I'm so mad. I'm so mad. I'm so mad. Oh my gosh. Should we read more of the dump? Do you want to keep suffering with me? I haven't read much further ahead. Let's keep going. Why not? Okay. So, oh, the other thing that he gets all up in his, like, I imagine him like pulling his pants up really high, like I don't know why, but he gets all like too big for his britches on, is like, they only did math. I'm like, yes? Okay, so okay, I'm sorry, I got tired. Okay. No, where did he say that they only do math? Is not no. Okay. Okay. And so they're mad about all this dating, by the way, because we use Milankovitch cycles and these like paleoclimate time series of like temperature data. We kind of use them to correct each other. Definitely using like Milankovitch cycles to, because those are pretty easy to calculate. And so you can use that to kind of like help calibrate. That's the word I was looking for. Help calibrate your like ice core or sea critter temperature reconstruction paleoclimate data set. Yeah, so utilitarian scientists, I hate that phrase. It just gives me an ick. Are now using Milankovitch cycles to extend an astronomical timescale in sedimentary rocks all the way back to the beginning of the Triassic period. So just using these is another way to kind of help us date things. There we go. So the paper's authors performed power spectrum analysis on data having presumed climatic significance. Again, it's a temperature proxy. Of course, it has climatic significance. Okay. The view is shared, blah, blah, blah. Okay, here we go. This is a quote from a paper by Alvarez. Okay. The widely accepted Kroll-Milankovitch theory that fluctuating climate conditions during the Quaternary glaciation have been driven by astronomical cycles is based entirely on time series analysis of paleoclimate and orbital data. What other data would you like to use? Is my question. Yeah, like the Milankovitch cycles are that, hey, these astronomical cycles cause major changes in Earth's climate over long periods of time. And that's supported by relationships between paleoclimate data sets and orbital data sets, like orbital mechanics, what other information would you like or would you want to show me that relationship? That doesn't make any sense. I thought there was a line in here that said they did, spectral analysis with this, like, I don't know, I read a emphasis on it. Like, well, they only did math. How correct can that be? And anyway, okay. Also inferred, when these data are plotted as a function of depth, many wiggles with occasional prominent peaks and troughs become apparent. So this is the isotope data. Oxygen isotope wiggles for the whatever core are illustrated in figure 2, largely because of power spectra of these data show dominant spectral peaks at frequencies corresponding to dominant cycles within the Milankovitch hypothesis. The paper was seen as providing strong support for the Milankovitch hypothesis. Yes. And that feels like that sentence is written with incredulity, right? Like, look, it's just wiggles. If you did a power spectrum analysis, what's that going to do? So for if anybody here is unfamiliar, a power spectrum analysis is you take a periodic data set and you apply a Fourier transform to it. And then Fourier transform, so you have a time series, and so you have like value versus time. So it could be like temperature versus time. I can show you a power spectrum thing. Hold on, because I did a power spectrum for my dissertation. So I have a couple plots ready to go, available in short order. Power series. I called it power series. Power spectrum is the correct term, but you'll forgive my titling of how I save my files on my computer. I write it correctly in my dissertation. It's labeled correctly in the actual dissertation. Okay, so let me show you how a power spectrum works. I have to share a different thing now. Present, stop screen, present, share screen. I would like to show you this guy, this friend, allow. Okay. So this is actually comparing two different data sets. I'm comparing the power spectra of two different data sets. But what I do is I have the daily change in sea ice concentration over like 40 years. And I am interested in where does it have significant power. So where it has significant power, so notice here my y-axis is normalized power, and my x-axis is a period of days, right? So instead of like time versus sea ice concentration, right, or sea ice concentration versus time, because you say the y-axis first, this is normalized power versus period. You could also plot it versus frequency, right? But which is the way it comes out of a Fourier transform. But period made more sense for me for what I was interested in. And this figure on the right is this figure, but it's zoomed in on shorter periods. And so I find this easiest to explain in terms of music, actually. So if I go to a piano and I play the note C, right, that corresponds to a periodic signal, like a sine and cosine signal, right, at a specific frequency. And I forget what middle C is in the specific hertz, right? And so if I were to take the Fourier transform of that sound, right, just holding out the middle C on a piano, then the peak, you would have a big peak like this. I don't know if you can see me circling that. Like dish. Yeah, okay. You'd have a big peak like this right at that frequency. So you have a lot of power at the frequency associated with the note middle C. Right now, if this was a like computer generated middle C, all of the power will be at that single frequency. But because you're playing it on a piano, on a real instrument, you also get these other harmonics. That's why a piano, a C on a piano sounds different to a C on an oboe, different to a C on a trumpet. You can tell the difference between those mathematically by where you're going to get these other important peaks, right? So most of the signal is at that one frequency of middle C, however many hertz that is. But then we're also getting some power, albeit less, right? There's less emphasis on these other harmonics, right? So maybe this is the frequency associated with like a G. Maybe this one is like the octave lower, stuff like that. So how much power is how much power is there is kind of a measure of like how important is this. And so what this says is in this sea ice, hey, there's a lot of importance at a frequency or a period relate at right around 365 days. Is there a periodic signal inside this big signal that would be at right at a year? Yeah, turns out. So this is just saying, hey, this data has an annual cycle, right? Because we've got this huge amount of power right at about 365 days. And then, oh, hey, what's this at like a half year period, right? So this guy and this guy at like this like 100 days and like 175. This is like a seasonal cycle that's also really important. And so this is, you could think of this as like the G harmonic to the C chord, the C major, the C note, middle C. Here's the root and here's the fifth. Here's the annual cycle, and then here's the seasonal cycles. Anyway, and then the important thing for my research, by the way, is that this is observations here on the right, and then this is model. This is model output. And so, by the way, this is all publicly available data, so you could recreate this if you wanted. So the types of sea ice loss events I look at happen at this like 20 days and less, at these shorter timescales. And if we notice, these curves here, the red and green lines, tell us something about significance. So like think about it's signal to noise, right? And so if the power is above those lines, then it's a signal, it's not noise. If it's below it, then it's noise. Or it is indistinguishable from noise. And so I'm interested in sea ice loss on these timescales. Look at that. Look at that. By the way, if you're wondering about this weird peak and like valley here that looks like a reflection, that's a product of I apply a 5-day running mean to this data, and so you get weird behavior at 5 days. Anyway, in the model output, oh no, there's no power indistinguishable from noise at those shorter time periods. That's all I'm trying to show with this plot. But anyway, that's what a power spectrum does. It tells you if I have a periodic signal or a signal with any type that I suspect may be periodic, and I do this power spectrum analysis on it. I do a power spectrum analysis on it. The power spectrum tells me where it has important peaks, right? And so if this, or where, at what periods or frequencies this data varies significantly. I guess that's a way to say it. So if you're using this to compare two data sets like I am, then I'm like, oh, hey, great. Look, this data has an annual cycle and this data has an annual cycle. This data has this at like 175 days, this seasonal cycle. This data has the seasonal cycle. Here's that like 125 days, 125 days, just shy of 100, just shy of 100, right? Beautiful. These frequencies, these periods are matching right up. And so I can say with a high degree of confidence that the model is capturing the same like physical changes over these long time periods as we see in observations. So if this was, let's pretend this is my Milankovitch cycles, right? we have significant power at a periodicity of 100,000 years and 40,000 years. Let's just pretend it's just those two peaks. And then this was my temperature data, and I did the same type of power spectrum analysis. Oh, hey, I also have significant peaks at 100,000 years and 40,000 years. And so that doesn't tell me, what is the phrase, a priori? That doesn't automatically tell me that these cycles are caused by these cycles, right? But it tells me, so it's a correlation, not causation type of relationship. But then if you know something about the physical system, like in this one, we're not looking for a causation relationship. I'm trying to see, does the model capture the same behavior as we see in real life? But if you know something about the data you're comparing and you have a physical reason or mechanism to believe that that maybe these Milankovitch cycles, there's a physical mechanism by which it could cause the type of thingamajigs, the type of climactic response that we're seeing in these temperature proxies, then you can write a paper that becomes very famous about it. And that's perfectly good methodology. So I don't know, like that's great methodology. That is basically just math, right? Like there is, that's not statistics. That's not like this thing is maybe related to this thing. That's like power spectrum is finding real things, right? Like that's a really good methodology. The math behind that is real sound. I hope that whole thing made sense. And so here's the paper again. This, like, largely because of power spectra of these data showed dominant spectral peaks at frequencies corresponding to dominant cycles within the Milankovitch hypothesis. Yeah, the paper was seen as providing strong support for the Milankovitch hypothesis. Like, yeah, why not? Like, again, that sentence, maybe I'm reading more attitude into it than is intended, but that sounds sassy to me. So for example, a place where this was done and then it turned out to not be true. Okay, so the nemesis hypothesis is one of my favorite things. I took a class in college, and it was physics and chemistry of the solar system, but we had to write a paper as part of the class, and it was write a research paper, a literature review style research paper, where you like review a real theory that was legitimately discussed in literature at some point in history, in the scientific literature at some point in history, that was since disproven. And it was very fun because you kind of got to see that scientific process and all of that. And so the thing that I wrote that paper about is called the nemesis hypothesis. And sometime in either the 70s, I think it was in the 70s, I kind of forget now. This was my sophomore year of college, and that was a minute ago. In geologic / paleontological records, there was thought to be evidence of periodic mass extinctions. So it was like, at the time, the data was saying it looks like every 26 million years or so, right? About that long, there is a mass extinction event. What could cause periodic mass extinctions, right? So this is there's this thing that seems to be happening frequently. So like, hey, there's these ice ages that seem to be happening every few thousand years, right? Like with regularity, with a periodicity, with a consistent periodicity. Now, this basis of the nemesis hypothesis is later overturned, right? So there is no paleontological evidence of periodic mass extinctions. But at the time, the data that they had suggested that was true. Notice this theory is overturned because better data is collected, right? And so it was already known that like the mass extinction of like the dinosaurs was caused by the meteor impact. And so then the question was, okay, so if there are periodic mass extinctions and the last one was caused by this type of event, let's suppose that they're all caused by that same type of event. So what would cause periodic mass extinction by asteroid impact? And so the proposal was that we are actually in a binary star system with a very sort of faint brown dwarf that we've never seen because its orbit is so far away, like beyond the Oort cloud. And in fact, every 26 million years or so, it would pass through the Oort cloud, is this hypothesis, sending like comets and like icy asteroids and things like that, meteorites careening into the inner solar system, and then some of them hit Earth and cause these mass extinctions, right? So wild hypothesis, but it was kind of the if that initial periodic mass extinction data was real, then this was the best explanation that they had, right? Now that theory was later overturned with better data, right? And I'll probably reference this a little bit more because I think we're going to stick with reading this paper for a little bit because I'm so upset. It made me so upset. And one of the things that he complains about in here is this idea that when you add data to the data set, the support for the theory grows. And he calls this like evolution of the data. Here we go. This new age assessment is extraordinarily problematic for the paper, as discussed below. Finally, the data sets used in the analysis have evolved over the years, raising the question which versions of the data are the real ones. And so again, I kind of like scanning ahead. I don't know where the exact thing is, and it might actually be in the first paper's summary of the arguments, but I'm not going to worry about finding like an exact quote right now. But basically, this author, Jakey Poo, seems upset that when they add more data to the data set, the relationship is strengthened. And he takes this as a, see, they're just making stuff up, right? They assume it's true and then add data and it makes it more true. And it's like a self-fulfilling prophecy, but like, no, because this is actually a comment you get from climate science deniers that drives me bonkers, right? Which is they're like some of the original climate predictions and like looking at global warming was just based off of like the data from the United States, right? We were seeing this prediction, and then when we added global data, the hypothesis became stronger. Right. The data that we added not only supported the original conclusion that we were getting warmer, but it actually like strengthened it. It said that, oh, we're getting even warmer than we thought we were. Right. And climate change deniers are like, see, they just added data to make it look like they were more right. It's like, no, my dude, we added data and we're like, oh no, it's worse than we thought. Right? It's like, I don't know, you bake a chocolate cake and you like, you hear the timer go off and then you forget about it. And then the timer goes off again and you're like, oh no, I left the cake in the oven too long. And you go in and you're like, oh no, you're concerned, like maybe it's burnt, right? And then you get into the kitchen and you smell, right? You smell the smell of like burnt sugar and you're like, oh no, I think it's burnt, right? And now I know I left it in the oven too long and now I smell that it's burnt. More data to support the same hypothesis, right? And then you open the oven and you look at it and you're like, oh no, I think it's burnt because it's black, right? And then you take a bite and you're like, oh no, it tastes burnt, right? So it's like we're just adding data. And it just so happens that all of the data that we're adding supports the original hypothesis, meaning that the original hypothesis was true. If we had heard the timer on our cake and we're like, oh no, I think the cake is burnt. And we walked in the kitchen and we don't smell burning sugar. And we open up the oven and it doesn't look black and charred, right? It looks like a cake should. And we take a bite and it doesn't taste burnt. Then our original hypothesis of the cake is burnt has now been proven false because we added in new data that contradicted our original data point, right? Which, by the way, the nemesis hypothesis not being a thing we talk about is proof that that's how science works, right? Like when hypotheses are proven false, right, or demonstrated not to be true, then we drop them and we're done with those now, right? Because science builds on itself and it's self-correcting, and that's what science is. And they're just big mad that like the more data we add, the more confident we are in this hypothesis. The more evidence, okay. I'm mad at it. I'm real mad at it. I hope you guys agree with me that this is very dumb. Remember that, do you agree with me? Do you agree with me that Jakey Poo doesn't know how seasons work? Like, it's not that hard to understand. It's just like, think about seasons and make that worse. Right? That's it. That's meh. Think about how winter works and then more of that. That's it. Like, it's not that complicated. You should go watch Miss Frizzle. Miss Frizzle will explain it to you, Jakey Poo. Okay. I think I'm done with this for right now. We are, by the way, going to jump in Journal Club, and we're going to read more of this. I think the rest of this first paper, because this is a 3-part series, is explaining how oxygen-18 sampling works, and we're not going to worry about that. I think we'll probably jump to this marine isotope stages and like the orbital tuning. Yeah, so like we'll go on to this orbital tuning and circular reasoning. I'm very excited to read that. And see what goes on from there. We'll probably try to focus on the problems, honestly, what his perceived problems are. And then we'll jump to, oh my gosh, evolving data sets. Oh my gosh, that makes me want to throw up a little bit. Okay, cool. And then we'll jump to part 2. So part 2 continues the discussion with an explanation of the technical details of the pacemaker analysis and partial application of the original results. And part 3 explores the effects that the above changes in timescale have on the original results as the implications for geochronology and the debate over global warming and climate change. I'm excited for this. So we'll take a break from the heat problem paper and go into this, because this is my wheelhouse. We're going to talk about global warming, climate change, all that stuff. Okay. Thank you so much for joining. I do really appreciate you guys. I'm happy we're spending a little time together. I'm going to go back. I think I am now going to make myself an adult beverage. And I've got to... Did I make those figures? I'm going to fiddle with my dissertation a little bit. Just a little bit. Not a lot. Just a little bit. And... sorry, this is the depths of brain fog and burnout that one experiences when you're T-minus 2 months from finishing your dissertation. You guys are great. I hope you have a wonderful day. Don't write a dissertation. Don't go do that. Go do something fun just for yourself. And I will talk to you soon, you beautiful little humans. Okay, bye, team. Also, sorry, I built this tiny robot. He's supposed to look like a centaur. And he's solar powered. And I haven't taken him outside yet. And my studio lights do not power him. Okay, now have a good day.